Good day. My name is Rowan Dominic S. G. Casol, and our group will talk about the type of sorting algorithm in the data structure, which is the quicksort. This presentation will consist of five parts, so which is this description, which I will talk about, in which I'll talk about a brief explanation of what the algorithm does and its main purpose. So for the visualization, we'll talk about a clear representation or flow of how the algorithm works step by step, which Mr. Harman will discuss. So for the efficiency, for Mr. De La Cruz, which is time and space complexity to measure performance. In the pseudocode explanation, which is for Mr. Naval, in which he will talk about the simplified version of the algorithm's logic written in pseudocode for clarity. And lastly, for the implementation, uh, a sample code showing how the algorithm is applied in an actual programming language, which Mr. Tan will. What is quicksort? Quicksort is a sorting algorithm based on the divide and conquer principle. It works by picking an element as a pivot and partitioning the array around it, placing the pivot in its correct position in a sorted array, while breaking the problem into smaller subs that are solved recursively. So a pivot is a chosen element used to divide a correct collection, while partitioning is the process or rearranging of the element around it. That pivot has already been turned into smaller elements. So in a simple explanation, it's like picking a toy, which is the pivot, and splitting the toy into smaller and bigger in groups. Then, in the smaller group, you will split it also. And after you split it, you will combine them everything back together. So it's like a recursion. So quicksort is used whenever we need to sort data quickly and efficiently, especially in software databases and data processing. Here are the quick sort steps on creating it. So step one, you will choose a pivot, which is in short you will pick an element. It's either first, last, or random. And then second, the partition, you will rearrange the array so smaller elements go left and larger ones go right. And then in the step three, recursion, which you will repeat the process for the left and the right subarrays. And lastly, for the base case, you'll stop when a subarray has one element and it's already sorted.
Well, essentially, quicksort is a fast sorting method, or in layman's terms, just piles everything up and then sorts it all the way to ascending to descending. And it chooses one item in the list to reference everything called a pivot. And then there's something that's called partition that arranges things and swaps the elements. And this rearranges the other items, which is everything smaller goes on the one side and everything larger goes on the other. And once this is done, the pivot is in its correct final position. Then the algorithm itself then repeats the same process on all the elements, and it goes both ways on left sides and right sides. When this is sorted, it uses the strategy rather that's been used in many times, such as Napoleon and whatever, called divide and conquer approach, which makes this efficient and is one of the fastest way to sort data on an average terms, even though it can be slower when the pivot choices are insanely inefficient. That's it.
For this part of the reporting, I'll be talking about the efficiency of quicksort. And for now, we will be talking about time complexity. The best case scenario is omega n log n. This occurs when the pivot element divides the arrays into two equal halves. Uh, what does this mean? In the best case, each pivot chosen divides the array into two equal or nearly equal halves. That means each level of recursion does O of n total of work for the partitioning process, and the recursion depth is O log n since the array keeps getting halved. In the average case, um, The pivot divides the array into two parts, but not necessarily equal. What does that mean? In the average case, the pivot typically divides the array into two reasonably balanced parts. Not perfectly even, but not extremely unbalanced. That means each partition step requires O(n) work to compare and rearrange elements around the pivot. The recursion depth is about O log n because the array size roughly halves each time. For the worst case of O(n squared, it occurs when the smallest or largest element is always chosen as the pivot. What does this mean? It happens when the pivot causes very unbalanced partitions at each step, like when the array is already sorted and the first or last element is always chosen as the pivot. For the next part, we will be talking about the space complexity of quicksort. The worst case scenario of O of n is due to the unbalanced partitioning leading to a skewed recursion tree recording a cost stack of size O of n. That means um, its space usage mainly comes from the cost stack. Uh, Quicksort is a recursive algorithm. That means each recursive call adds a new stack frame which stores things like the start and end indexes or indices of the current subarray, the pivot value, and the local variable. For the best case scenario, which is O log n, is a result of balanced partitioning leading to a balanced recursion tree with a cost stack size O log n. Uh, that means the space usage mainly comes from recursion, not from extra arrays. Each recursive call handles one subarray, and when the pivot splits the array evenly, the recursion tree becomes balanced. So that means each recursive level handles smaller halves of the array, and the recursion depth equals the height of the recursion tree. That means, and you get O log n.
Okay, so my name is Matthew Saiming Naval, and I will be explaining the pseudocode for quicksort. So first, we have the quicksort function. So here's what's happening. So the condition if low is less than high, make sure we only run the algorithm when there is more than one element to sort. So we then call the partition function, which will arrange the elements around a pivot and return the pivot's final position. We call this pivot index. So once we know where the pivot ends up, we recursively call quicksort again for the left side of the pivot. That's from low to pivot index minus 1. And for the right side of the pivot, that's from pivot index plus 1 to high. So this way, the algorithm keeps breaking the array into smaller and smaller parts until every part is sorted. So now, let's move on to the partition function. So here's how it works. So we pick the last element as our pivot. Then we set I to one position before the start of the subarray. This marks the boundary between smaller and larger elements. Next, we loop through the array using j. So for each element, if it's smaller than the pivot, we increase I by 1 and swap array I and array j. So this makes sure that all smaller elements stay on the left side of the array. So after the loop ends, we swap the pivot with the elements at I plus 1. So this moves the pivot into its correct sorted position, with all smaller values to its left and all larger values to its right. So finally, we return the pivot's index. So to summarize, pick up pivot, which is the last element. So next, put smaller numbers on the left and bigger numbers on the right. Third is place the pivot in its correct position. And number 4 is repeat the process for both sides until everything is sorted. Thank you.
Good day, I'm Dwayne Tan and I'll be reporting about the Quicksort sample code and its implementation that we made. So, to start off, the code works by relying on three main components: a swap utility, the primary sorting logic in the partition function, and the recursive control flow in the quicksort function. The algorithm takes the unsorted array H3170102 as input and it produces the sorted output 0123710. The partition function is the functional core responsible for the partition step. It chooses the last element of the current segment, the array high, as the pivot. It then initializes a pointer I, which acts as a boundary for elements smaller than the pivot. It iterates through the array segment with pointer j. If an element array j is found to be less than the pivot, then I is incremented and that element is swapped into the position of the array I. This ensures that all elements confirmed to be smaller than the pivot are kept on the left. Finally, the pivot is swapped into its correct final sorted position, array I plus 1, fulfilling the goal of placing smaller numbers on the left and bigger numbers on the right. So let's now talk about the quicksort function. The quicksort function is basically what governs the recursion step. It checks the base case if low is less than high. If the segment has 0 or 1 element, the recursion stops as the array is considered sorted. If low is less than high, it calls the partition to get the pivot's final index. It then makes two recursive calls to itself, one for the left subarray, which is low to pi minus 1, and one for the right subarray, which is pi plus 1 to high. This continuously breaks the problem into smaller subproblems that are solved recursively. So lastly, now for the main function, which is basically what provides the execution for the whole code. The main function simply sets up the problem, it initializes the unsorted data, calls quicksort to start the process, and it prints the final sorted result. So that's basically the explanation for the whole sample code and implementation. Now let's go ahead and proceed to the conclusion of the whole report.
So why is this important? Quicksort is important because it uses one of the fastest and most efficient sorting algorithm, especially for large amount of data. It helps computers organize information quickly, which makes others tasks like searching, comparing, or analyzing data much faster and easier. Also, it it is being used in a real life situation and functions. Like for example, in database, it is being used to sort records and data entries, making searches and lookups faster. In search engines, in which it will help organize search results or data in the indexes efficiently. For the e-commerce websites, search products by price ratings or popularity checks, and others like data analysis and visualization and system applications. So that is all. Our group members is Tan, Dwayne, Saul, Ronan Dominic, De La Cruz, Clark, and Adrian, Harme, George Krian, Naval, Matthew, Simic. And that is the quick source. Thank you.